So, hello everybody. Let's start and continue with our topic in macroeconomics. Today we are going to discuss two different things. First of all, I will continue with our discussion of the ISLM model. However, last time we did the graphical discussion and representation of the ISLM model. Today I will do the analytical representation. And that is interesting because last time we just discussed what happens if there is an interest rate cut. And then we saw, well, the LM curve shifts to the right. But this was just telling us the direction. Today we are also interested in how far shifts the curve to the right. And to compute how far, obviously we need numbers, we need equations. So I will discuss the whole ISLM model we discussed last time graphically. Today we will do this in a kind of mathematical way. And the second topic of the day is the open economy ISLM model. So we will study the same we did last time for the closed economy, but we take into account what happens if we open the economy. So what happens if we have exports and imports? So these are the two topics of the day. So let me start with the first topic, which is the ISLM model, an analytical discussion. The outline of this part is divided in 5 parts. First of all, I will quickly recap what we did last time. Then I will show you how to handle and how to do the total differentiation of the goods and the money market. Then we have to solve these two markets. And I will do this with a so-called matrix transformation. Then I solve the matrix equation. I do after that the re-transformation. And then we will use the solution of the ISLM model to discuss, for instance, a monetary policy stimulus. So this is my plan. So let me start, first of all, again, what is the ISLM model about? In particular, the graphical and the analytical representation. So last time you all learned that the goods market can be represented by the so-called income expenditure identity. And that is Y output or income in our economy is equal to private consumption, investments, government spending, and in an open economy, we also have to consider net exports. That is what we will do in the second part today. First of all, we assume once again a closed economy, so net exports are 0. There's another interesting point which is different here to some other representations so far. First of all, I say the investments, well, usually they are dependent on the interest rate. As we know, it's a downward sloping curve in respect to the interest rate. And therefore I say, well, investment is a function of R, our interest rate. And the second new point in this equation is that consumption is a function of income minus T, and that is the taxes. And that is what we call in economics the disposable income. You can say net income, so income after tax. Yeah, that is usually the income you have for consumption. It's the income you get minus the taxes you have to pay. So this T is representing a tax function. And this tax function consists usually of 2 parts, or this transfer function of a state consists of 2 parts. One is the so-called income tax, this little t, which is paid on your income, Y. And then there is a second component, which is independent of income, tau. And this parameter is usually a transfer. So for instance, if you have a family, if you have kids, if you are unemployed, you get transfer from the state. Yeah, so somehow you can say the tau is a negative number, it's a transfer, it's a money inflow. And if this inflow, if this t function is substituted in here, you see there is income minus taxes. And if the transfer is negative, then the transfer adds. Minus and minus is plus, adds to your income. So this is a more general representation of the goods market, that consumption is dependent on disposable income. For the next 15 minutes, once again, when I do the computation on the blackboard, I assume that the taxes are 0. That makes the calculations a little bit simpler, but you can generalize the whole calculations with a tax function. And in my lecture notes, you will find the calculations with the tax function. Therefore, I explained it here explicitly. The second equation we learned is a money market equation. The money market equation, once again, consists of two sides, supply and demand. And money supply is given from the central bank. It's exogenous. M over P is the real money supply. And on the other side, we have money demand, as you all know. And that is the liquidity function or liquidity demand. And that is dependent on two parameters. One is income. And keep in mind that last time we discussed the relationship between liquidity demand and money is positive. So the higher my income, the higher is the liquidity demand. And the second component of the liquidity function is the interest rate. And last time we discussed here the relationship is negative. So the higher the interest rate, the lower is my liquidity demand. The more money is on my bank account because I have a higher rate of return there. Yeah, so there's a negative relationship between these two interest rate and the liquidity demand. So this is what we studied last time. And now what I do next, I will use these two equations. Equation 1 represents the goods market. Equation 2 is representing the money market. And I will discuss the issues we discussed last time graphically, today analytically. So before I do this representation in an analytical fashion, let me recap it here in the corner. One case we discussed graphically last time. So I hope you remember the graphical representation of the ISLM model is in a graph where we have output and real interest rate here. And then we said, well, there is this downward sloping IS curve, and there is an upward sloping LM curve. The LM curve is representing all the equilibria in the money market. The IS curve represents all equilibria in the goods market. And then we have an equilibrium point, let's call it E0, and that gives me my output in this point 0 and my equilibrium interest rate R0. That is the ISLM model. And keep in mind for the, I skip here the full employment line, which is usually vertical lines through this equilibrium as well. So for simplification, I just look to the ISLM and these two markets. Okay, and then we studied, for instance, last time, what is happening if there is a monetary stimulus. That means the central bank is pumping money into the market, so the money supply increases, or in other words, the central bank cuts the interest rate. So what is going on? Does anyone remember the impact of a monetary stimulus, more money supply?
Yeah, in the short period, we have higher output present.
Yeah.
Higher output. In the long run, we are going back to the
Yeah. So what happens in the short run in this graph?
right.
The LM curve shifts to the right, exactly. So in the short run, we have a new LM curve, LM prime, and that is due to a expansion in money supply. And that leads to a new equilibrium point, call it E1, and as you already said, increases our output from Y0 to Y1, and we have this interest rate R1. So this is what we discussed last time. But we don't know how far does the LM curve shift to the right, right? Does it shift just to the right here, up to here, or even further? And therefore, today we are studying this market in an analytical fashion, using these two equations. And what we do basically, we use these two equations to find the equilibrium point, and then we study what happens with this equilibrium point if there is a change, for instance, in M. And what happens if we change the money supply to my output variable? So what is the impact of the change in income? and what is the impact of the change in the interest rate. And by this you already see what we have to do first. When we try to discuss this model analytically, we use the two equations, and let me now write down the two equations which are here on the slide. The goods market equation, call it equation 1, which is income is equal to consumption dependent on my income. Once again, I skip the taxes here, plus the investments dependent on the interest rate R, plus government spending, closed economy so far. This is the goods market. And then the equation 2 we have to look at is obviously the money market, which is representing by money supply, real money supply, M over P, and that is equal to the liquidity function, which is also dependent on income, Y, and then R plus the expected inflation rate. And to make this the computation even simpler, let me assume that the expected inflation rate is very small, or let's say it's close to 0. It is equal to 0. And then we can simplify also this liquidity demand function just to write a second factor, the R. It's just a simplification. Does not change the results here. So if we plan now to use these two equations to study the equilibrium point, well, then you see we have two equations. We just have to find this intersection point in a simple way. But what we are interested in is not just this equilibrium point. We are interested in what happens with this equilibrium point if there is some change of my policy variables. So the money supply is the policy variable of the central bank, or the government spendings is a policy variable of the government, fiscal policy. So we want to know what happens if we change either M or G on this equilibrium point, and in the end, on output and interest rate. And to figure out what happens, what we have to do with these two equations, we have to find the so-called derivatives, because a derivative is representing the change of the variables. So my next point is now do the total differentiation of the goods and the money market equation. We already have the goods and money market equation here. And now we do the total differentiation. So that is my second point. Yeah? Total differentiation of the goods and the money market. This is standard calculus, you can say. We compute now the total differentiation of my goods market equation. What is that? First of all, the derivative of y is 1 times the change of my y is dy. Then we compute the derivative of my consumption function, which is c prime of y, times the change of my variable dy. Then we compute the change, the derivative of my investment function, which is I prime of r. That's the first derivative, times the change of my parameter r, dr. And then we compute the derivative in respect of g, which is exogenous, is 1, times the change of government spendings, which is just dg. This is the total derivative of the goods market equation. You always compute the derivative in respect to every parameter, every variable, times the change of this variable. That's the rule. And now we do the same for the money market equation. Once again, you can follow me and see how it works out. We compute the derivative in respect of m. Then this derivative is 1. P is treated as a constant times the change of m, dm. Now we treat the m as a constant and we compute the derivative in respect of p. Yeah, p is in the denominator, so the derivative is then due to if I bring the p up, there's a minus in the exponent, so it's m over p squared times the change of dp. That's the first derivative in respect of p times the change of dp. That's the left-hand side. And now we compute the derivatives of the right-hand side. Here you see there is a function dependent on two variables, and therefore we have to compute the partial derivatives. So we compute the partial derivative of the liquidity function in respect of income, the first one, times the change of income, plus compute the derivative of the liquidity function in respect of the second component, which is the interest rate R, times the change, dr. That's it. That's the total derivatives or differentials of the goods market equation and the money market equation. Why is this important? And why did we compute this? Well, the reason is, keep in mind, we are interested in what happens if we change money, the M, which is now here. That is a change of money supply. Or what happens if we change government spendings to our variables we are interested in, to the change in output and the change in interest rate. Output, change in interest rate. That is what we are interested in the end. And therefore it is necessary that we use these two equations, do the total differentials, and now we have two equations in two unknowns. And what are the two unknowns? Well, it's the output, the change in output, that is what we are interested in, and the change in the interest rate. So we have now to rewrite these two equations in a nice way, and then we have to solve it for the change in output and the change in the interest rate. So let me in a next step just rewrite a little bit and collect terms. So I want to have that all dy terms are on the left-hand side and also all r terms. Yeah? So I want to have all dy terms on the left-hand side and all dr terms and anything else on the right-hand side. So let me bring this term to the left-hand side, and then I can extract out of a bracket. So let's call it I prime. So that's a next step. I bring this term on the other side, and then I have 1 minus the consumption function dy, because I have two dy terms. One is this, the second component with the minus is this. And then I bring the r term also on the left-hand side. Here it's plus, on the other side it's then minus. So I prime of r dr. And that is equal, what remains on the right-hand side is just the government, the change in government spendings, dr. It's just algebra. Yeah? Moving these two on the other side and see that dy is in both components, so bring the dy outside the brackets. I do the same for the second equation. Here it's quite simple because, well, here's dy and dr. It's just on the other side. So let's rewrite the second equation just the other way around. Put this on this side and what is here on the other side. Yeah? So, and maybe I can simplify the writing of these fractions. Instead of writing always the partial derivative of my function in respect of y, let me use this. I just write L subscript y, and that is the same as the partial derivative of the liquidity function L in respect of y. And I do the same definition short for here. L subscript r representing just the derivative, the partial derivative of the liquidity function in respect of r. Then I can write down here L subscript y, which is this, times my variable dy plus L subscript r times my change variable dr. And then on the other side, I have this term, which is 1 over p dm minus m p square dt. P. The reason why I did this, well, now we see we have two equations in two unknowns, and the two unknowns, once again, is dy, the change in output, and the other unknown is the change in the interest rate in the ISLM model, dr. And now you can really see that this is a system of two equations in two unknowns. And this is the unknown, it's dy, and the second one is dr, the change in output, dy, and the change in the interest rate, dr. So what we have to do next, this is my next point on this list, the matrix transformation. That's what we did. So now let me transform these two equations, the total differentials of these two equations, into a matrix to solve the system of two equations in two unknowns. To solve a system of two equations in two unknowns, there are different ways. One way is the method of substitution. Yeah? You solve the first one in respect of dy, and then you substitute this in here, then you solve it for dr, and so on. But this is it's very complicated due to the long equations. So the simplest way to solve this equation is not by substitution, it's by transformation into a matrix. And that is the process and the idea I want to show you here. So, third, matrix transformation. So, what I'm going to do next is the following. I just write down these two equations in another way, in a matrix. There's no calculations, it's just another way to represent two equations. How does it look like then? Well, we will see that we will have a matrix, then we have a vector, and this vector is representing these two unknowns. And the first unknown is my change in output, dy, and the second unknown is my change in dr. And then we have the equal sign. And on the right-hand side, well, we have once again a vector, and this vector is representing these two sides. On the top, the change in dg, and on the bottom, we have this, 1 over p dm minus m over p squared dp. So now we have to find what is in my matrix here in the beginning. Well, the matrix is representing the right-hand side. And for the first line, we will have the elements of the first equation. So the dy term is here in the first position. So this is 1 minus c prime of y. That is the corresponding term to dy. In the second position, we write the second term of the first equation, which is minus I prime of r. And now you can already see that the first equation is given, because the first equation is first term in my matrix times first in my vector minus second term in matrix, second term in my vector is the second component equals dt. So the first line in my matrix is now the same as the first equation. It's just another way to write it down. And now I do the same for the second. Well, you see dy term is the L subscript y, and for the second component, it's L subscript r. That's it. Now we have transformed the two equations into a so-called matrix equation. The reason why I did this has to do because this is now relatively easy to solve in comparison to the solution of these two equations with other methods. So this is a matrix. Let's call this matrix A. Yeah? So I give the whole matrix a letter A. And then we have a vector. Let's call this vector B. The vector B is the unknowns, right? So I want to know what is happening with the change of my output and with the change of the interest rate. So that is what we are interested in the end. And then on the right-hand side, I also have a vector, which is, let's call it Z. So in a simple way, you can now write down this matrix equation in a very compressed way to say, well, this is my matrix A times my vector B is equal to my vector Z. Why not? And as I already said, we are interested in what is B. So that is the vector we are interested in. And the question is now, how can we find this B, given we have such an equation? A times B is equal Z. And in the end, we want to have B is the only parameter on the left-hand side, and everything should be on the right-hand side. Well, in calculus, you would just say, well, we have to bring the A on the other side, right? We just divide by A here, then it cancels, and then we divide by A because it's an equation on the right-hand side, and that's a solution. Yeah, that is right. However, A is a matrix, and therefore we cannot divide by a matrix, but we can multiply with the inverse matrix on both sides. And if we do this on both sides, then we have inverse matrix times matrix is the so-called identity matrix, and that is 1. Yeah, this is like canceling out each other. It's 1. And then we have just the B on the left-hand side. And what remains on the other side is, well, the inverse matrix times my vector Z. And that is the solution of my matrix equation. So what I have to do now with this matrix equation, well, on the left-hand side is in the end my vector B. And on the right-hand side is this. And in front of this vector, the vector Z, is my inverse of this matrix A. So I only have to find the inverse of matrix A. And fortunately, for a 2-by-2 matrix, the inverse is quite easy to compute. And that is what I will show you next. So we compute the solution of this matrix equation. So, next step. Let's solve the matrix equation for solution. So as I already told you in the previous part, the solution of my matrix equation in the end gives me my vector B, which is the vector of the unknowns dy and dr, and that is equal to the inverse matrix. So keep some space to find this inverse matrix. Even here in front we need some space. That is in the end my inverse matrix. I call it A minus 1. And then we have in the second position this vector Z, which is the right-hand side of my equation. We already know this vector Z. That is the same as it was before. That is 1 over P dm minus m p squared dp. So the only step, the only computation we have to do to solve this is the inverse of my matrix A. And what is now the simple rule, as I told you, for a 2-by-2 matrix? The inverse is quite simple. The rule is the following. Can I go back a step and look once again to my matrix A here? The rule is the following. The inverse is computed by change the elements on the main diagonal. What is here comes up here. What is here comes down here. So first, change the element on the main diagonal. So this comes up here, and this down here. That's the first step. And the second step, change the sign in front of the off-diagonal element. So here's a plus, then we write down here a minus, and here's a minus in front, that turns into a plus. That's second step. And then the final step and third one is, and therefore here in front there is something, divide and multiply this inverse matrix by 1 over the determinant of this matrix A. These are the 3 steps you have to do. Let me repeat. To find the inverse matrix, the rule is change the elements of the main diagonal. That is what we did. Change the sign of the off-diagonal elements and multiply the whole matrix with 1 over the determinant of A. What is that? That is the only and final point I have to clarify. So what is the determinant of my matrix A, of this matrix down here? And here you can see why it's so important to learn something about mathematics in one of the first classes. So what is the determinant of A? The rule is the following. Multiply the elements of the main diagonal minus the multiplication of the elements of the off-diagonal. So let me write down. I multiply the elements on the main diagonal, which is this first element times second element, multiplication of these two, minus the multiplication of these two elements, Ly, times, here's a minus, and this minus, well, that turns into a plus times E prime R. This is the determinant of my matrix A. So let's, for 1 minute, look to this determinant of my matrix A. And what I'm interested in is the following. First of all, I'm interested in the sign. Is this determinant positive or negative? And secondly, I already want to tell you that in the end, this is a number. Why is this a number? Well, the derivative of my consumption function, if you remember what we did last time, this is always, that's the so-called propensity to consume. It's a proportion you consume. For instance, you have income 100 euros, and then you consume 50 euros, then the propensity is 50%, 0.5. And that is actually this. So this C prime is representing the propensity of consumption. And we can estimate this for Germany and for any other country because we have data about the consumption of households that is collected by the statistical offices. So we can estimate this linear regression, and then we have a number for this. We can estimate also the slope of my investment function. You know, the investment function is downward sloping. So we take a look to the statistical office. They collect the data of investments and the interest rate. We can do a linear regression, and we find the slope of this downward sloping curve. It's a number. And also these two parameters are numbers, because this is the first derivative of my liquidity function in respect of the interest rate. We have data about the liquidity in our economy. We have data about the interest rate, linear regression, 2 variables. We can find the slope. The same is here, the linkage between income and liquidity. We have data about income, we have data about liquidity, linear regression, and in the end, all these terms turn into numbers in reality. So what is now this number? Is this number positive? Or is this number negative? So take a look. The investment function is a downward sloping function. So the slope is negative. No question. Also this term, I think, is clear. The propensity to consume is always a number between 0 and 1. And therefore, 1 minus a number between 0 and 1 is always in the same interval, 0 and 1. It's positive. Yeah, it's between 0 and 1. This is a positive term. What is the derivative of my liquidity function in respect of the interest rate? R. Can you remember last time I gave you the examples? I'm in front of the cash machine, and if the interest rate is high, then I keep the money on the saving account. Yeah, so there's a negative relationship. The higher the interest rate, the lower is my liquidity demand. It's a negative. And the second example was, well, the higher the income, the more liquidity demand. This relationship is positive. Now take a look. Positive times negative gives me a negative number here in front. And then we add also a negative number. So a negative number plus a negative number is definitely something less than 0. So my determinant is negative. That is what I want to have here. And that is actually what turns out. So to keep this in mind, you can write down just here a minus sign, and then you always know that the determinant in this case is always negative. And you will see this helps us later on to do the discussion. Okay, now the final step here is to do the retransform of the solution in matrix form back to two equations. So what I do next, I retransform this matrix solution into equation 1 and equation 2. And equation 1 is representing the change in output, you can say the goods market, and the equation 2 is representing the money market and the change in the interest rate. So let me write down now these two equations. First equation starts with dy is equal to, then on the right hand side the first term is 1 over the determinant of this matrix A, and then brackets. And now we use the same rule as we applied a couple of minutes ago when we did the transformation into a matrix. First element in my matrix times first element in my vector. So it's L subscript R times dt. Then second element in my matrix is the I prime of y times second element in my vector. 1 over p dm minus m p square dp. Take a look again. This equation is now representing the first line in my matrix equation. That's the retransform. Now I have transformed back from the matrix to the equation. And now we do the same for the second line in my matrix equation. The second line is dr. And then we have once again 1 over the determinant of this matrix A, which we know it's negative. Then we make a bracket. First element in the second line in my matrix is minus Ly times the first element in my vector dg. Second element in the second line of my matrix is 1 minus c prime y times second element in my vector, which is this guy here. 1 over p dm minus m over p square dp. These two equations represent the retransformation from the matrix on the top into two equations back. The first equation tells me now the solution on my output, on the change on output, dy, that's a change on output, given some change of the variables here on the right-hand side. And the second equation tells me the solution of the change in interest rate in my ISLM model, given some changes of the variables here on the right-hand side. So this is the final solution, the general solution of the ISLM model. And now, what I'm going to do next is I use these two equations, which represent the solution, to make the same discussion we did in the beginning graphically. And I show you that a monetary expansion, an increase in money supply, leads to an increase in output. So we will see that dy is positive, that is an increase. And we will see a monetary expansion leads to a lower interest rate, so a declining interest rate. That means dr, the change in the interest rate, is negative, it declines. Okay, final step. Let me now discuss the analytical ISLM model, and I will discuss a monetary expansion. Step 5, discussion. And the discussion I will do here in class is monetary policy, and I will discuss a monetary expansion, so an increase in money supply. That is what we did in the beginning graphically. And I will do this discussion now analytically based on the solution we have computed in the past minutes. So if there is an increase, if there is an increase in money, then the change in money, which is represented in my calculation by the dm, that is the change in money, well, that is positive, right? There is an increasing money supply. The money supply tomorrow is greater than the money supply today. That means the change is positive. And if you take a look now to the first equation here, then we see, well, this dm is positive. But what is going on with the change in the price level and with the change in government spending? Well, in economics, we always assume, in a simple fashion, the so-called ceteris paribus assumption. And ceteris paribus means we just take a look what happens if we have a change in money supply. Anything else is the same. So we assume there's no change in G, no change in government spending. And therefore, if the government spending is the same this year and next year, well, the change is 0, right? If the government spends 100 this year and 100 next year, then the change, 100 minus 100, is 0. So in this discussion now, we will see that this term is 0. The change in dm is non-zero. That is what we really change. And in the short run, Keynesian assumption, we assume the price level is the same. It's also 0, short run. Yeah? So we study monetary policy in the short run first. And given that, we can now write down equation 1 in a simpler way, because this term, 0 times something, is 0. So what do we have then? We have the change in my income is 1 over the determinant of the matrix A. This term is 0 plus the investment function, or the derivative of the investment function, times, well, the first term in the bracket is non-zero, so it is 1 over p times dm. And then we have to multiply the investment function to the second term. But once again, the second term is 0, because we assume, ceteris paribus, short run, the price level is the same, and therefore the change is 0. Well, this simplifies, for monetary policy, this equation to this one, in case of monetary policy. Now let me rewrite this again. This is the same as, on the left-hand side, we have the change in output. And now you see all the factors are multiplied. Here now let me bring this dm, the change in money, on the left-hand side. So then we have the change in output is equal to the change in money supply, and that is equal to 1 over the determinant of my matrix A times the investment function times 1 over P. And this is down here. Yeah, I just multiply by 1 over M, cancels out here, and then it's here. So now we have this equation. On the left-hand side, this is telling you what happens if the money supply changes with my output. It's a derivative. It's dy over dm. And that is determined by what is here on the right-hand side. So let me take a look. What is the sign on the right-hand side? Well, the determinant is negative. The price level is always positive. The slope of the investment curve is negative. It's downward sloping. What is then the overall sign? Negative number times a negative number is something positive times positive. Yeah, well, that means the right-hand side is definitely greater than 0. And if the right-hand side is greater than 0, then you know if money supply increases, if we have an increasing money supply, then positive relationship output will increase. If money supply increases, output will increase. So what we have here derived graphically is now what we can see from this equation analytically. And the benefit, and that's the reason why we did this, it's not just to show that this is right, what we did graphically, it's also to make clear, in the end, these terms are numbers. We know the price level, we can estimate the slope of the investment function, we can compute the determinant, as I already told you. You have a number here. And if this number, let's say, is 2, and you pump 1 million into the market, then the impact on output, if this is 2, will be 2 billion, right? So now you actually are in the position to compute the quantitative effect of this shifting of the airline curve to the right. Yeah, if you increase money supply, let's say by 1, and suppose the numbers gives you a 2, well, then you know the effect on output will be twice. If the number is just a half, we don't know the numbers here so far, then the effect is just €500 million. So you see that with this analytical approach, we can get also a quantitative idea of these effects of a monetary stimulus and a fiscal stimulus. Now, from the second equation, we can compute the impact on the interest rate R. Yeah? Let me do this for our monetary policy case. Once again, we assume if we discuss monetary policy, there is no change in fiscal policy. So the change in my fiscal policy variable G is 0. There is a change in monetary policy. In short run, price level is fixed. This is 0 as well. Now let me write down for monetary policy the second equation in this simpler way. So the change in interest rate is 1 over the determinant of my matrix A. This term is once again 0. Then we have the second term, which is multiplied with the first component in the bracket, which is non-zero. So it's 1 minus C prime times 1 over P dm. And then once again, this second component multiplied with the second component in the bracket is 0 again, because we assume in the short run, price level is fixed. So we have this for the interest rate change. And now let me write it down like this here on the top. I multiply with 1 over m on both sides, then this turns up here. Then I have dr over dm is equal to the remaining elements here. It's 1 over the determinant of a. Then I have 1 minus the consumption function times 1 over p. Once again, we are interested in the direction and the sign of the change of the interest rate if we change my money supply M. To see the sign, we have to look to the right-hand side. The determinant is negative. Price level is positive. These are obvious. What is the sign of this? 1 minus the propensity to consume. Positive, because the propensity is a number between 0 and 1. So it's positive as well. And now take a look to the overall sign. Minus number times a positive is negative, times a positive still. So that seems to be a negative number. Right? And that is telling you, if you increase the money supply, the interest rate, negative, should go down. And what we see graphically, yes, that's the case. If we increase money supply, the LM curve shifts to the right, but the equilibrium interest rate is after that lower than before. Yeah, negative relationship. More money, lower interest rate. So this second equation is actually showing what has happened here graphically for the interest rate. And once again, at the end, you can put in numbers here by estimating these functions, and then you have an idea what is really happening with the interest rate if you pump 1 billion, let's say, money into the economy. So this discussion is showing you, once again, let me sum up. This discussion is showing you the ISLM model in an analytical representation. First of all, we have seen from this discussion that what we find here in mathematics, in analytical equations, is the same what we did last time graphically. So it's consistent. It fits our graphical discussion last week with the today's calculations. And secondly, the reason why we did this computation is sometimes it is important to know what is the size of this effect if we change the money supply or if we change government spending. And to see the size, the number, well, we can't see this from our graphical discussion, but we can compute now these effects from these equations. So the question is this the way how policymakers or central bankers really compute the effect of a monetary stimulus or a government stimulus in praxis? So do policymakers really use these equations, and then if they decide let's pump 1 billion into the market, then what happens with my output? What happens with my interest rate? And frankly, no, they are not using these equations, because this model, even it looks for you very complex, is far too simple. Yeah? First of all, it's a short-run discussion. Secondly, there's no labor market in it, right? We assumed they're out. Then we assume closed economy. We assume there's no tax system, to make it simple, and so on and so forth. So this is a model which is just good for students to show, well, in the end, you can compute the size of a monetary stimulus and a fiscal stimulus, but in praxis, the policymakers, they have far more complex models. And these models, the policymakers are using in praxis are called dynamic, stochastic, general equilibrium models, in short, DSGE. These models, far more complex, far beyond what we can do here. That is what the policymakers are using to compute what is the effect of a monetary stimulus on output and what is the effect of a monetary stimulus to other economic variables. These models, they have sometimes 3,000, 5,000 equations and not just 2, as we discussed here. Okay, so the question is, can we also calculate what happens if we have a government stimulus, a fiscal stimulus package implemented by the government? Yes, of course. So if you discuss this for, I would call this fiscal policy, yeah, a stimulus by the government, well, then you assume that the change in government spending is non-equal 0. It's positive, yeah, if they increase, or if they implement austerity measures, then it's maybe negative. And then we assume anything else is 0. The change then in money supply is 0. And in the short run, the change in the price level is 0. And then what you have to do, you have to use the solution, which is here, for this constellation. Yeah, then this remains for fiscal policy. You have this term. This is 0, this is 0, though the second term is 0. And then you can write down the dg on the other side. You have to see what is the size of these two factors, the sign and the size. And then you know whether income goes up and income goes down. Maybe that's a good homework. Yeah? And you can compare this by looking what happens graphically. So what would you expect? An increase in government spending, as you know, shifts the IS curve to the right. So what do you expect? You expect an increase in output, so dy should be positive, and you expect an increase in the interest rate. So if you plug in these two conditions in the first equation, in the end, this term you get here should be positive, increasing, and the term you have here should be positive as well, because the interest rate is also going up. Yeah? So this, for the interest rates, then remains. 0, 0 is gone. So you have to look to what is the size here, what is the sign here. This is negative, is positive. This is positive. You see immediately a positive number remains. That means an increase in government spending leads to an increase in interest rate. And that's what you can see graphically. And you can also discuss, obviously, for instance, what happens in the longer run, right? If you assume, well, the price level is non-equal 0, yeah? Because the price level adjusts up or down. I just looked here to the short run. Because the computation is not so important, that's off the record here, okay? The computation is not so important for us here. Yeah? So for me, it's far more important that you really understand how the graphical model works, and that you have just a kind of overview that you can also do the computation and you can see then the size of these effects. So let's continue now with the next topic, the open economy ISLM model. And we will see that the open economy ISLM model is very close to the closed economy ISLM model we already discussed. There is only one new factor, and that is the so-called net export factor in the goods market, which is representing or defined exports minus imports. But on top of this, we have to understand what is really affecting the number of exports and imports in an open economy. And we will see from this quote by Calvo, which is a famous macroeconomist who once wrote something about the open economy, that the key element when we look to exports and imports, so the linkage between the domestic and the international economy, is the exchange rate. So to really understand how an open economy works, we have to get a better understanding what is an exchange rate, what are different types of exchange rate, and how does the exchange rate influence the exports and imports in general. And that is what we are going to do next.